So to conclude our discussion of brick and concrete in the Roman world, we'll turn to what is maybe an even more familiar work in Rome than the Colosseum, and certainly one that is structurally more impressive. Even though it's a smaller building, the span here is something like 42 meters, is much, much greater than anything in the Colosseum, right? Which, as we said, was made of simple barrel vaults kind of lined up one after the other. The Pantheon is a clear span, and as such, it has structural interest in ways that go beyond the sort of smaller spans of the Colosseum. One giant span instead of dozens and dozens of smaller ones. The Pantheon, or the temple to all gods, was built originally in timber, we think, by the Emperor Agrippa in 25 BCE. And the ultimate construction was done by the Emperor Hadrian, who succeeded Trajan in 117. His architect, Apollodorus, worked for Hadrian after working for Trajan, although there's a legend, one that is probably apocryphal but too good to be true, that Hadrian remembered Apollodorus making fun of him trying to draw before he was an emperor, and then prepared some drawings of the Temple of Venus to show Apollodorus that he didn't need an architect. Apollodorus pointed out that the door of the temple was too small to let the goddess out, and so the goddess would be trapped in there. And Hadrian had, as a result, allegedly had Apollodorus executed, right? So a client-architect relationship gone wrong. Apollodorus seems to have worked on the project for the reconstruction of the Pantheon, the building that we see there today. And it is impressive both for its scale, but also for the way that it intuitively resists the thrust of the dome, that it holds the dome up, but also keeps it from flattening out and collapsing. There are tricks to the Pantheon that resonate with those that we saw in the Colosseum by the Emperor Vespasian. The dome is coffered, so there are areas of the dome that are basically carved out, which lightens the dome considerably. And we know that they incorporated aggregate made of tufa, this lightweight volcanic pumice stone toward the top that help reduce the weight of the dome as well. The base of the dome, the cylinder that supports it, has gigantic niches in it that today are chapels. The building was converted to a Catholic church in the 7th century. That niched wall provides the buttressing that keeps the dome together. And we'll talk a little bit when we look at a section about why it's not a dome in the modern sense, in that it doesn't have anything inherently to resist the what we call hoop stresses at its base. Instead, it relies, like a barrel vault does, on a very, very thick wall to be a literal physical buttress. And there's a story to the facade that harkens back to our discussion, not of brick and concrete necessarily, but more of stone, and that shows some of the problems that would have faced Roman builders in terms of procurement. The building is famous, of course, for having this 43-meter diameter space inside, and it's a spherical space, a semi-spherical space sitting on top of a cylindrical space. But the kind of perfect proportions of it are achieved by the fact that the dome is essentially half of a sphere, where if the North Pole is at the top, at the oculus, the South Pole would touch exactly the center of the floor below. And the shape of it very clearly relates to this idea of all gods, right? Of a kind of internal universe that's perfect and complete on its own. Much of the decoration that we see today was added in the Renaissance, but you get a sense for the space at least. And the coffering, even though it's been plastered over several times, is certainly original. So the idea that all of the gods are celebrated here, that they maybe each have their own niche within the thick cylindrical wall at the base. You can see just how thick that is. It's about 6 meters thick. And when you look at this section, you can get a sense for how much work that external wall is doing in terms of being a buttress for the dome, resisting the thrust of the dome at its base. The proportions extend to the treatment of the dome. This is the coffering that basically divides the dome into a series of ribs, basically taking some of the dead weight of the dome's thickness out of it, but also introducing an architectural motif that visually makes the dome seem more impressive, right? That adds a sort of forced perspective. And the oculus at the top, of course, the light from above, the light from the heavens. This had not only the functional use of providing illumination to the space below, but also, of course, had this cosmic or spiritual connection, right? Very much like the pagoda was a way to link the earth and heaven. The sort of function of a temple in Rome is to link earth with the gods, and the oculus in this case is the way that's done. A void instead of a solid, as in the pagodas, but still an effective linkage. Now, as Robert, Mark, and others have pointed out, the dome of the Pantheon, it has a fairly sophisticated set of structural principles behind it, not all of which its builders would have fully known. The shape, of course, is part of the game here, and it gets thicker and thicker toward the base. The stepped rings on the exterior help make the dome kind of thicken out. It's not a single thickness, but it gets thicker as it gets toward the base. And you can think of that either as almost sort of a cantilevered shape, right, that gets bigger toward the root. Maybe a better way to think about it is that all of that extra thickness is acting like the stones in the triangle of the arch in the aqueduct that we looked at. In other words, it's surcharging the structure, putting weight right where the thrust is at its worst, and that is helping to deflect the resultant down toward the vertical. So it's lessening the amount of thrust that the dome experiences. On the right, you can see that the gravity system is largely composed of these relieving arches that we talked about when we were looking at brick lintels. Arches that are built into the wall that essentially direct the weight or the load of the structure's mass down onto the thicker parts of the niched wall below and allow for these voids within the wall. That makes for a lighter structure on the foundations, but it also makes for these functionally useful chapels around the perimeter. And here, as you can see, those are completely hidden, right? We don't see those except on the exterior, where what we think was probably travertine had been taken off. You see in this section 2 that it repeats the trick of the Colosseum, where the materials themselves get lighter and lighter as you go up the structure. So the top of the dome is made predominantly with tufa aggregate, large blocks of pumice in the concrete, and then as you come down, the concrete is populated with bricks, broken tiles, until down at the base you get more travertine, right? So the structure gets heavier and stronger as it comes down to the base. How you build a concrete structure like this? You require centering that was probably had to be to scaffold the entire space at once, right? Because it's a monolithic dome. You can see here proposals for how that might have been done. Large-scale timber scaffolding, it would have required an enormous amount of wood to build the centering to make the surface that the concrete could have been placed against. A couple of ideas for how that worked. There are other ideas that suggest that the dome would not have to have been poured monolithically, and that it might have engaged a temporary formwork or scaffolding that might have traveled around the perimeter. In other words, you fix the top center of the scaffold, you fix the base against what would be the top of the surrounding wall, and then you simply place the concrete on one segment at a time as you go around the perimeter. Now, today, that's not the way we would do a concrete dome, because we want it to be monolithic. We want it to be hyperstatic. We want it to be all one piece so that the forces can flow through it in multiple directions. But as Robert Mark has pointed out, the end result of the Pantheon dome is that it's not in one piece. All of that plastering on the coffering is there for a very good reason, and that is that there are gigantic cracks in the Pantheon dome, some of which are like 6 or 7 or 8 inches thick, that would probably frighten people if they saw them from below. So the interior surface has always hidden those. Those cracks have been there since ancient times. And if you think about the arch theory, right, where we were looking at arches that displaced their buttressing walls and could still survive perfectly intact so long as there are no more than those four hinges. Well, the dome of the Pantheon and other ancient domes seem to behave the same way. And this is Robert Mark's idea about how when that dome is built and when it settles for the first time, once it cracks, there can't be any tensile hoop stresses at the base, and the dome actually stops behaving like what we would call a shell structure today, and is actually acting instead like a series of radial arches. Each one of those arches is structurally independent, right? Each piece of the orange is structurally independent, but each one of them has enough wall on either side to buttress it, to resist the horizontal thrust and to keep it standing. And this is very common in the Roman domes that survive. We see these cracks that run along the radial dimensions of the dome. The domes stand fine. It's just that they're not exhibiting the kind of three-dimensional behavior that we expect out of our domes today. They're simply acting like a series of arches that are arranged radially. And Mark goes on to say that he thinks that the use of concrete, which we generally think of as structural, in ancient Rome, this suggests that it was more about the construction, right? More about the act of building rather than the structural performance of concrete. Mark thinks that they assumed that the building would behave like this, that it would behave like a series of arches, and therefore the choice was whether to do it out of concrete or brick or stone. Either of the three would have worked structurally. He thinks that the cost of laying the concrete, since it could use unskilled labor, probably conscripted labor, made that choice much, much cheaper than brick or stone. And he thinks, therefore, that Roman concrete, even though we think of it as structural, actually was used more for the process of building instead of for the final performance. Addis points out that the imperial Roman construction advanced sort of humans' ability to build in ways that we keep having to remind ourselves were truly incredible. The precision of the layout of the Colosseum or the Pantheon is really remarkable given the tools that they had, right? Ropes and pegs. And yet the layout is very precise, even of a fairly complex four-centered oval, as you see in the Colosseum. The fact that brick and concrete, and in some cases even iron, was manufactured and used in building construction suggests a very sort of modern way of thinking about fabrication. The Romans were lucky to be on a volcanic peninsula, so they had access to this kind of magic dust, pozzolin, that allowed them to use hydraulic cement. Their basic invention of the arch and barrel vault and the groin vault, I would add to that, and the methods of centering and supporting those both reveal that their kind of engineering know-how was tremendously advanced, right? More than any of the other building cultures that we've seen. And it's clear that they used a design process. When you look at the layout of the Colosseum, that oval is not something you would have come up with on site. That's probably something that you would have at least rehearsed in drawing form. We looked at the Roman ability to engineer stones to move around great weights and move them to great heights. And maybe most impressive was the administration, right? Managing the logistics of all of this material, the millions of bricks in the Colosseum, the tons and tons of concrete that went into the Pantheon, and organizing the ballet of workers that went into that. So even though we kind of look at the monuments of this era and are impressed by kind of the objects that got built, Addis points out that really we should be paying attention not just to the nouns, but also to the verbs and the methods of construction that went into these. So I'll close with one sort of fun fact about the Pantheon that goes back to our lecture on stone and the Romans' use of stone from abroad, in particular from Egypt. The Pantheon has two pediments. one of which is the pediment that is actually built, that extends from the front and that's supported by these large Corinthian columns. But the other one is this kind of ghost pediment on the mass of the building itself, right? And you can see it sort of graphically on the facade, but certainly not built out, and clearly not intentional, right? There's a mismatch between the pediment as built and what was clearly anticipated. Now, this has posed a puzzle to architects and historians and classicists ever since the Renaissance, at least, and there are all sorts of reconstructions showing what must have been intended, from the top one here, which is the full pediment at that higher ghost pediment level, to others who thought that there was some kind of intermediate entrance that must have been planned and then abandoned for whatever reason. But Robert Wilson Jones, in an essay that I've included in the readings, suggests that the pediment, or the portico as built, was the result of a well-known shipwreck that occurred in the Mediterranean about the time that the Pantheon was being built. The theory is that the order for the taller granite columns that would have built the portico at the right height was lost with this particular shipwreck, and that the builders of the Pantheon had to make do with locally sourced columns, possibly spolia or columns dragged from another project that weren't the right height, right? That they weren't able to get the properly scaled columns for the Pantheon. And the alignment of this kind of like clear mistake, when you look at the elevation, and this one shipwreck that appears to have involved a shipment of granite, suggests that the Pantheon was victim essentially to a supply chain issue, and that it would have taken far too long to get a new set of granite columns excavated, fabricated, delivered to Rome from Egypt. They had instead to rely on locally available but much smaller columns. From here, we'll look at these traditions of domes and of vaults, groin vaults in particular. We'll look at another set of Roman constructions, Roman imperial constructions, that go beyond even the impressiveness of the Pantheon's dome, and that really point the way toward future construction, both in the Byzantine Empire and in medieval building as well, that rely on the kind of skeletal nature of the groin vault and take it in directions that sort of begin with a very, very clearly Roman building, but that will end with something that is utterly transformed and completely new.